So we've been discussing how call context sensitive points to analysis is more precise than context insensitive analysis. But now, I'm going to introduce a new idea by first showing the limitations of call context. So recall this example of a program which has a memory class which has a field called M, and this is the main program that sets M with two different objects of different derived classes, and then finally calls getM and then calls virtual function. And we saw how a call context sensitive analysis with a context depth of 1, call context depth of 1, is able to precisely identify that this f is d1's f and this f is d2's f, where f is the virtual function and d1's f and d2's f's are the two implementations, and statically the compiler can figure out that these are actually d1's f and d2's f, and that can allow it to generate faster code at the dispatch of these functions. And the reason for that was because the call context at each of these call sites of setM were different, so ld1 and ld2 in this example, and so the object pointers were versioned based on the call context, so ld1 and ld2, and as a result the corresponding updates were also versioned based, so sm was versioned using ld1 and ld2, and correspondingly the objects were updated, the corresponding versions of the object were updated. For example, if through this dispatch it was this ld1 that was updated, and through this dispatch it was this keyword's ld2 version that was updated. And that's why we got a precise answer. But let's say I change my example a little bit. And let's say setM does not directly update M, but setM actually calls a helper function H, and H now updates M. So I've just increased the call depth on this path from setM to H to the actual information to 2 from 1. And now the call context sensitive analysis will become imprecise, as I want to show you quickly, if the call context depth is only 1. Of course, the analysis becomes precise if if you increase the call context depth to 2, but increasing the call context depth to 2 has a multiplicative factor increase in the running time of the analysis. It can go from n to n square, for example. And so that is usually not done. And no matter what call context depth you use, I can always create a program where it's going to give you imprecise results by just engineering the call context depth or the call depth, the calling depth or the call stack depth to be greater than that call context depth analysis is call context depth. So let's look at this example where I'm going to analyze this example with a call context depth of 1. Then the first thing I need to do is I need to give this call site a label. So let's say this call site is LH. Now I'm going to label all the variables based on these call sites in my call context sensitive analysis with depth 1. And so this means that this variable in setM is going to be versioned using ld1 and ld2 call context, because ld1 and ld2 are the two call sites. Similarly, this variable in getM is going to get versioned using the two call sites lr1 and lr2 of the getM function. And this variable of h is going to get versioned with its call site. And there's only one call site for h, which is LH. Even though LH, the setM may be called through two different call sites, h will only be called through one call site. And so there's only one version of this variable in h, and that's this LH. And this is going to be the problem, this is going to be the precision issue in our example, because both M1 and M2 are going to be potential pointees of this LH, and because of that we will basically say that M1 may point to M2's fields and M2 may point to M1's fields in our over approximate conservative points to analysis. Okay, let's see how this is going to work. So this is the original solution without H. Notice that here the getM's this was pointing to M1 and in context LR1, and getM's this in LR2 was pointing to M2, and the corresponding allocation sites are L0M1 and L0M2, where 0 represents the call context of the top level main function. Similarly, this set M LD1 and this set M LD2 point to the respective objects, and as a result we get a precise answer that R1 can point to a D1 object and R2 can point to a D2 object, and so we can resolve their virtual function calls precisely. And this is the original solution when there was no H, the helper function H in the memory class. But now, because of the helper function H, what happens is that this variable in the helper function, so this helper has only one version, as we saw previously, which is the LH call site, or one context in which it's called. And because it has only one context and it's actually being called on two call site paths, so this variable can point to either an M1 object, which is represented by this call site, that allocation site L0M1, or to an M2 object, this is L0M2. And so this is the first place where you kind of see something that's kind of point to both M1 or M2, and this imprecision causes more imprecision in our fixed point solution. So when we do more transfers, we're going to say, okay, so when we transfer across this dot M equals SM or HM in the helper function. So recall that there's a statement called this dot M dot equals HM. So this LH can point to either M1 or M2. And so it seems like, and so HM on the other hand could point to either, so HM would have, let's say, two versions. Actually, HM can only have one version, but so eventually what happens is that it appears like L0, the M1 object can point through the M field to the D2 pointer, because there's only one version and we are only tracking one version of this and one version of HM. So it appears, and because this LH can point to either M1 or M2, it appears, and HM can also point to either D1 or D2, it appears that M1 can point to D2 and M2 can point to D1. And this kind of accumulates the imprecision that was caused because of this first imprecision that we saw, which is the single version of this pointer in helper. Okay. Finally, because of this imprecision, when we actually do the getM call, then it appears that this the M variable of this pointer can point either to a D1 object or to a D2 object. So as a result, when we do this fixed point computation further, we see that R1 as a result can point either to a D1 object or to a D2 object, and this is represented by these extra edges from R10 to L0D2 and R20 to L0D1. And this is an imprecise solution because now the compiler cannot statically resolve the calls to the virtual function f. Okay, so what was the problem? The problem was that when there was a call to the helper function h from set M, the call context changed from, let's say, LD1 to LH, or in the other call path LD2 to LH. Now, can you avoid this? Well, one approach is to increase the depth of the call context, but we already said that that's going to be too expensive. Well, one idea here is that, okay, instead of a call context, let's use some other context that makes more sense or is likely to yield better results. And notice that you can actually group these contexts any way you like. And usually we engineer these contexts carefully such that they capture a maximum number of, they give you most precision for the least amount of running time of the analysis. And one idea here is that you use an object context. So if there's a transition from one function to another function within the same object, then we assume that the object context does not change, even though the call context in this example changed, because the call site changed, the last call site changed, but the object in which the context of this object under which I'm still executing has not changed. And so that's what I'm going to call the object context, and this likely would work better than call context, at least in object-oriented languages, because this kind of helper function calling pattern is very common in such languages. Okay, so the basic idea of object context is that you track this object under which the function body is being analyzed. And if this object remains the same, then we keep that context of this object with us. And this is only possible for object-oriented languages. And the rationale is that the program's behavior will likely be similar within a single object and different across different object contexts. Okay, just like call context was a heuristic idea which may or may not work. The object context is also a heuristic idea which may or may not work. There are examples where object context will work worse than call context, and then there are examples where object context would work better than call context, as for example the last example that we saw. But in general, for object-oriented languages, it is typically the case that object contexts work better than call contexts. Okay, so how do you assign an object context? Well, recall, just like for call context, we need a finite number of statically identifiable contexts. In the case of call context, we would just look at all the call sites and say, these are all the call contexts that I want to consider. If it's depth 2, then I'm going to look at all the 2 depth call contexts that can potentially appear in the program. Similarly, I need to have some way of identifying statically a finite number of object contexts. But recall that the number of runtime objects is unbounded. So the same function may be called, an unbounded unbounded number of object contexts, because there could be different number of an unbounded number of allocations of a particular class, and for each of those objects of that class, you can invoke a member function. So there is an unbounded number of runtime objects. But we already know how to deal with something like this. We use abstract objects to represent the call object context. So we basically group all the objects that are allocated, let's say at an allocation site, if we are using an allocation site abstraction for the abstract objects, under the same abstract object. Okay, and we use that abstract object as the context under which a member function of that object is being evaluated. Okay, so let's see that with an example. So in this example, this is an allocation site, LM1, and this allocation site will act both as an allocation site, as we've been doing that for identifying abstract objects and using them as nodes in a points to graph, and also as an object context for member function calls through that object. So for example, M1 is an object that has been created. When I say M1.setM, then because M1 is belonging to the abstract object LM1, setM will be analyzed in the abstract object LM1. If M1 represents an object that could belong to potentially multiple abstract objects, possible, then we analyze setM in all those abstract object contexts. In this example, setM is called only in a single abstract object context, so it's going to be analyzed in that case, in that context for this call. For this call, it's going to be analyzed in LM2's context. Similarly, at this call here, it's going to be analyzed in whatever is the abstract object corresponding to M1, which is again LM1. So getM will also get analyzed in LM1 and LM2 due to this call. So I've written this here. setM is analyzed in two contexts, which is LM1 and LM2. H is also analyzed in the same two contexts, because when you make a transition from setM to H, this time we are not going to look at the call site for context, because this is an object sensitive analysis. We're just going to look at what was the abstract object corresponding to this pointer of at this call at setM. And in this case, it will be either LM1 or LM2, depending on which one it is. It will call H under the same call context, so which will also be either this LM1 or this LM2. And similarly, the call object context for getM would be this LM1 or this LM2. Recall that when we were doing call context, then we had this LD1 and this LD2 for setM, this H for H, and this LR1 and this LR2 for getM, because that was a call context. Because now we have changed the definition of what a context is, the object contexts are completely different. And notice that the big improvement that we have in this example, at least, is that now we have two object contexts for the function H. And we know, depending on where it's flowing from, it's going to be, precisely identifiable that, okay, this is actually referring to an M1 object, and this is actually referring to an M2 object when we actually run our points to analysis. So that's a basic idea. Now, on the left, I show the solution without the H function at call context depth 1 that we had seen in our previous module as a precise solution. And on the right, I will try to build the similar solution with the H function using an object of context. So recall that our program had these allocation sites, M1 equals new memory, and this was LM1, and then M2 equals new memory, and this allocation site was LM2. And just like before, we basically say, because of the, by virtue of these two allocation statements, say M1 in context 0, and 0 represents the context of the main function, the object context of the main function. So because main does not execute in any object, so we just use the 0 object context for the main function. So the M1 0 may point to an allocation performed at allocation site LM1 in context 0, because that's where I'm analyzing this memory. Similarly, M2 0 can point to LM2 0, and this is exactly the same as we were doing for the call context. However, there is a slight difference. Because we are going to assume that the object context has depth 1, I'm going to forget the last context when we do an allocation site. So unlike the call context where we remember this context 0, in the object context I'm going to forget that context 0, because after all, when I go to another object, then or to another object context, I cannot keep track of all the object contexts through which I came through, because I need a finite number of object contexts. And so assuming my object context depth is 1, then and I'm going to later discuss how to deal with k depth object context. But if my object context depth is 1, then I'm going to replace the 0 with M1, because 0 was the old object context, and because of the new allocation, and the allocation itself represents a new context, so this is going to be LM1 instead of L0M1 as it was in the call context case. Recall, the call context increases the context across a call. In object context, the context increases because of an allocation, and so that's why while here we keep the context, here we do not. And similarly, M20 points to LM1. Okay, now let's continue and build the points to graph for this example. So by virtue of this new D1, I create an allocation site LD1, just like I did LM1. And because by virtue of this dispatch, I say SM in object context of the abstract object corresponding to M1, which is LM1. So that's why it's called SM subscript LM1 can now point to the object that was allocated at LD1. So this is the corresponding edge that gets drawn because of this dispatch. Similarly, SMLM2 can point to LD2. And recall that when we do this dispatch, then we also update the formal the dis pointer in the across this kind of member function dispatch. So the dis pointer for setm is, let's say, this setm being analyzed in the object context of M1, which is LM1. And that can point to whatever is the receiving object, which is M1, which is represented by abstract object LM1. So this setm LM1 can now point to LM1. Similarly, this setm LM2, so this setm in context LM2 can point to an object allocated at location LM2. So that's because of this dispatch to setm. Now, this function setm is going to call H under its own this pointer, which is this setm. And so we're going to see again two pointers added, two edges added to my points to graph. One is by virtue of this argument SM to HM. So whatever SM LM1 was pointing to, HM LM1 will also start pointing to. Now notice here is the improvement in precision. The context of HM is whatever was the context of SM, or whatever is the context of this, more precisely, this setm LM1, which is just LM1. Okay, or whatever this setm LM1 could point to, and so that's HM LM1. When I say a context of a receiving object, I really mean that what if it was this pointer, then what could it point to? In this case, M1 could point to LM1, and so LM1 becomes the context of this function setm. Similarly, here LM2 becomes the context of setm. If M1 could point to multiple objects, then all of them become a context of setm, and I need to update I need to kind of do these transfers for all those contexts independently. And in this example, there is only one context, but later I'm going to show you rules where we have what happens when we have multiple contexts. So in this case, M1 has M1 is pointing to a single object LM1, so that's why we got SM of LM1. If there were more, we would have also updated those SM version for those abstract object contexts. Similarly, HMLM1 can now point to whatever SMLM1 was pointing to, which is LD1. Similarly, this h lm1, so this is the this of the h function in the same context lm1, because that's where I'm coming from, can point to whatever this set m lm1 can point to, and that's again lm1. And the same thing happens for the m2 object. Finally, we execute the m equals hm function. So when we execute the m equals hm function, this one, then we draw an edge from whatever this could point to whatever hm could point to, like this. And if it's a field sensitive analysis, we label it with m. The same thing happens here. And finally, this is my final solution. I guess now we need to worry about get m. So maybe that's in my next slide. So, and then when you do the get m, then you basically look at, so when you do get m here, then this get m, lm1, can point to whatever m1 can point to. So that's this. And this get m lm2 can point to whatever m2 can point to, that's this. And then when you reference this dot m in get m, then you just follow the m edge here, and it can only point to LD2, and this can only point to LD2. So that's my next slide. So when you dereference this dot m, then you basically say that R10 can point to whatever this get m lm1, whatever it can point to, and then like 2 hop from there, that's LD1. So R10 can point to LD1, and similarly R20 can point to LD2. So this is the precise solution that you can obtain using an object sensitive analysis for this example. Even in the presence of multiple helper function calls, there could be arbitrary unbounded number of helper function calls within a single class to its own functions, and the object sensitive analysis would still work without having to increase the depth of the object sensitive analysis. This solution that I have on the right is as precise as the solution without the H helper function using call context. And I hope this example also throws some light on why we expect an object sensitive analysis to work better in practice, at least for object oriented languages.